In this video we're going to look again at polynomials, but we're going to look at polynomials in what we call factored form. So, I'm missing a letter here. Recall, the standard form of a polynomial look like this. So a to the n, x to the n, plus a bunch of other terms depending on the size of the polynomial. So that's what we call the standard form. We also had the standard form, so a specific polynomial of a quadratic function was this: f of x equals ax squared plus bx plus c. And this is something you're familiar with going back all the way to grade 10. But we probably, or hopefully remember from grade 10 is that this function here often wasn't the most useful form. So, however, it was often more useful to change the quadratic to what we called factored form. And a factored form of a quadratic, if you remember grade 10 at all, a big part of it, grade 10 was factoring quadratics. So the factored form was you take this thing and you convert it to, the leading coefficient would be factored out, and then you'd have two brackets, x minus some number r, and then the other bracket x minus some number s. Why was this useful? So one reason it was useful was it helped us find the zeros or the x-intercepts or the roots. All those mean the same thing, or the same thing in different contexts. Helped us find zeros, roots, x-intercepts, which if you remember, those were just the r value and the s value. So let's just do a couple examples just to remind ourselves of what that means. So find the zeros of these two functions. Well, in order to find the zeros, you would have to let f at x, that's what a zero is, right? A zero is when f at x equals 0. So we have to set f at x equal to 0. So we're going to write f at x is equal to 0, x squared plus 5x plus 6, and then you have to solve for x, or figure out which values of x this is true for. So the way you're going to do that is to factor. So the way we factor this is we come up with the two numbers that multiply to the constant and add to the middle coefficient. So product must be 6, sum must be 5. So those two numbers are positive 3 and positive 2. So that would be the sort of factored form. So now you have 0 equals this thing times this thing. So we're multiplying two things, and our product is 0. Well, the only way the product of two things can be 0 is if one of those things is 0. So either x plus 3 must equal 0, or x plus 2 must equal 0. Simply solve these simple linear equations. So x is equal to negative 3, or x is equal to negative 2. So now we know the two x-intercepts are zeros, and that would help us graph, right? If you wanted to sketch this original function here, we could just plot the x-intercepts. So there's an x-intercept at 2, and there's an x-intercept at 3. And then depending on how accurate you want to be, you could get more information. Like, for example, we'll know that the y-intercept is 6. If you subbed x equals 0 in here, you'd get 6. So we could make sure we hit the y-intercept of 6. You also know the vertex occurs between these 2 points. So between 2 and 3 would be 2.5. And you could figure out what the y value is. My accuracy would just be to connect the points like this, so I know that's as accurate as I'm going to get. So very loose sketch, very rough sketch, where I hit the y-intercept and the two x-intercepts. So the function looks something like that. This one over here, if I wanted to get the x-intercepts, again I'd set f at x equal to 0 and factor this. So in this case, two numbers that multiply to 4 and add to 2. Well, the two numbers there are 2 and 2. So it's the same number. And actually, if you remember, this is what we call a perfect square, meaning the two factors are the same. And usually you wouldn't even write the two factors separately. You'd write 0 equals x plus 2 all squared. So if you have the same factor, generally it's best to go straight from here to here, just to save yourself some time of writing this step. I never make a big deal about if you do write this step, but I'll tell you right now, some teachers do. So just be aware of that if you ever have a teacher who doesn't like to see you write this intermediate step. So now you just have one thing that's equal to 0. So if x plus 2 squared is equal to 0, that means that will occur when x plus 2 is equal to 0, right? If you square something and you get 0, that means that thing must be 0, which means x must equal -2. So we only have one x-intercept. So hopefully you remember why that occurred. So that occurred because your vertex was right on your x-axis. So the vertex at -2 was right there. And in this case, we had a y-intercept of 4. And that's enough for accuracy. So I'll just kind of, again, a very rough sketch. Okay, so that's how factored form helped us with quadratic functions. So it's useful for quadratic functions. Now, it may be helpful if we could generalize this factored form to higher degree polynomials. So just a couple things to talk about before we try doing that. So notice in this factored form, for this one, you had two distinct factors. So the degree on both these factors was 1. And this one, you had one factor, but the degree on it was 2. So I mean, there's two factors there, but it's the same factor. That's going to lead us to a new, well, just a new term, sort of. And that's what we call the order of the factor. So the order of a factor. So the order of a factor is just is the exponent is p, is the exponent to which the factor is raised. So basically, how many times does that factor occur in the algebraic, when it's in factored form? So in this case, you have two factors. X plus 3 is one factor, and its exponent is 1. So this one has an order of 1, and this one, the order is 1. And for this one over here, you had the exponent was 2. So x plus 2 has order 2. And in this one, x plus 3 and x plus 2 both have order 1. And why this is going to be significant is because it's going to tell us a lot about the graph. Notice that a factor, two factors that have order 1, the zeros in those cases go through the x-axis, right? Go right through the x-axis. When it has an order 2, it just touches the x-axis once. It doesn't actually cross it. So actually what's happening here is, or the way we think about it is, order 1 is kind of like a degree 1. Remember, degree 1 means a polynomial, or a linear. And a linear is just a straight line. Well, you might be saying, okay, that's not a straight line. But if you zoomed in really closely, so it's like a zoomed in view of this x-intercept. So there's your x-axis. And here's the function crossing the intercept right there. So really close to this x-axis, or to this, if you zoomed in very close, it looks like it. If you zoomed in close enough, it would end up looking like a straight line. Whereas this one, if you zoomed in around the x-axis here, so if you zoomed in there, So there's your x-axis, there's your 0. When you zoom in, it still looks like a quadratic. It still looks like a parabola, which is of degree 2. So an order 2 looks like, when you zoom in, looks like a degree of 2. Looks like a parabola very close. Whereas this one, an order 1, looks like degree 1. So next video we're going to look at sort of how you can generalize this to cubics.